Well, there are several ways in which the features of the interest points can be calculated. The texture features can be calculated. The most important of them being the Sift descriptor, which is widely employed for these kind of applications. And the main motivations of using the Sift descriptor are as follows. So the Harris operator is not invariant to scale changes in the images, and if we want to make a comparison between two image patches, it is not even invariant to rotation if correlation between the patches is performed. Then for a better image matching, Louis, who is a researcher, his goal was to develop an interest point operator that is invariant to scale and rotation changes in the images. And also he aimed to create a descriptor that was robust to variations corresponding to typical viewing conditions. Well, these viewing conditions can have different aspects. For example, the affine changes, combined rotation and scale changes should be easily handleable. Then, as far as the viewing conditions are concerned, an important variation that can take place is the illumination changes in the images. So all these, variations, they have to be effectively handled to be able to find descriptors which are robust to any imaging conditions. The descriptor. The descriptor which gives us invariance to a lot of these imaging conditions is Sift. And now this is the main idea of employing Sift. So this is one signature image that we have, and this is a transformed image that we have. So from the signature image, we apply some corner detection technique like the Harris corners. We calculate a descriptor, and then based upon that descriptor, we find that this is how we describe this particular image region. So for all the interest points that we have found using any interest point detector, we basically find the image descriptors. Now we apply the corner detection methods on the new image, and then once we have obtained those the corners, then we calculate the same descriptor for all the points that we have obtained. Now, if you remember the last time when we were discussing about the Harris corners, one of the main optimization, or one of the main points of consideration was that we should always be able to reproduce the same point again if the algorithm is run, even if the different viewing conditions have changed. So we should be able to reproduce the same the same interest points. So this is the main assumption here. If we have captured interest point over here, we should be able to capture it over here. We have captured some interest point here, we should be able to capture them over here as well. And then later on, if we want to do any task, for example, image matching, we simply match these descriptors from the signature image and the novel image, and then we match the image regions. Well, we have several advantages when we are using Sift. The first one, locality, which means that the features are local, so they are robust to occlusion and clutter. We do not require any prior segmentation, which is once again a big research challenge. Then the distinctiveness of the features, which mean that the individual features can be matched to a large image database of the object. So these features are so distinctive for different scenarios that we can have different features representing different scenarios. So the distinctiveness is a very important property. Then the quantity, well, there are many features that can be generated for even very small objects. Then, as far as the efficiency is concerned, we have a close to real-time performance. And last but not the least, the Sift features can be easily extended to a wide range of differing feature types. We can add robustness. We can add several other important characteristics to the Sift features. From a top level, the overall procedure of applying the Sift image descriptor is as follows. So at first we compute the scale space extrema, which means that we search over multiple scales and image locations. The second thing is key point localization. And by this, what we mean is that we fit a model to determine the location and scale, and we select the key points based upon a measure of stability. We'll obviously discuss about this in detail. Then the orientation assignment to compute what is the dominant orientation of a particular interest point, and then the description of the key point in which we use the local image gradients at selected scale and orientation to describe the key points in detail. So the procedure for the calculation of space extrema is as follows. We already know the goal, so we have to identify the locations and scales that can be repetitively assigned under different views. The method is that we need to search for stable features across multiple scales, and previously work has been done using the Gaussian function. And basically, the scale space of an image is a function that is produced from the convolution of a Gaussian kernel at different scales with the input image, as we have already discussed about the scale space pyramid. This is how it looks like. We always start at the bottom level from the original image, and let me go on to the next slide. So in this mean pyramid, what we do is that from this original image we go on to the second level, which is a subsampled version of the original image by calculating the mean of 4 pixels in the original image and assigning this mean value to one particular pixel. So this is how we reduce the resolution of the image to half, and then from here on we further reduce the size of the image to half once we go on to the third level, and so on. This is how mean pyramid is constructed. Whereas we can also have a Gaussian pyramid in which we always start with the bottom level, that is the original image, and we apply a Gaussian filter to this. And at the second level, each pixel is the result of applying a Gaussian mask to the first level and then subsampling to reduce the size. So we need to filter at this level. At first, we need to apply a Gaussian mask, and then we need to perform the subsampling of this image. The advantage is that if you remember about the frequency domain, if we want to subsample an image, we need to perform pre-filtering. So you can say that first of all we smooth out the image contents, and then we keep on subsampling the image if we want to go on to different levels. The next step is to calculate the interest points, which is usually done by the Laplacian of Gaussian kernel. We can use different values of standard deviation to find different Laplacian of Gaussian kernels that will effectively manipulate with the width of this Laplacian of Gaussian kernel. And as we can already see over here, a small example where we are trying to identify the blobs corresponding to the location of sunflowers. We can see that that there is a perspective viewing in this particular image because we are standing on one side of the field, and the flowers which are closer to us will appear to have bigger blobs in the center, whereas the sunflowers which are far away from the camera, they'll appear in smaller size. So all these flowers will respond to different standard deviations, are going to respond to different Laplacian of Gaussian kernels with different standard deviations. So this is the main advantage of having different scaling parameters of the Laplacian of Gaussian kernel. As far as the pyramid scheme is concerned, we have a space that is separated into octaves. Octave 1 uses scale sigma, then the octave 2 uses scale 2 sigma, and so on. In each octave, the initial image is repetitively convolved with Gaussians to produce a set of scale space images. These Gaussians, they have different standard deviations. Now, adjacent Gaussians, they are subtracted to produce effectively the dog filter responses, which is the difference of Gaussian responses, or effectively we can use only the Laplacian of Gaussian responses also with different standard deviations. Both options will give us nearly the same results. And after each octave, the Gaussian image is downsampled by a factor of 2 to produce an image that is of size 1/4 as compared to the previous octave, and then we repeat this procedure for the next octave and so on. This is how the pyramid scheme works. Now a visual demonstration of the pyramid scheme, as we have already discussed. So these are the original images which have been filtered by Gaussian filters having different standard deviation, and then the consecutive filtered images in the system, they are subtracted from each other, and then we find these lattices. So these are effectively difference of Gaussian filtered responses. Then we have the next octave where the image is downsampled by a factor of 2 both in horizontal and vertical dimension, and then the same repetitive procedure is adopted over here. Now the next thing is the key point localization, in which we want to detect the maxima and the minima of the difference of Gaussians in the scale space, and that is done by comparing one particular pixel along with all its 8 neighbors in the neighborhood in the same scale, um, and then the same pixel is also compared to 9 other labels to 9 other neighbors in the scale above and the scale below. So this is the strategy for the selection of key points or doing key point localization, and it should be noted that this will give us a stable key point, and there will be chances of having repetitive key points with small changes taking place in the images. Mainly the key point is going to be more stable in this case. Now, with regards to the key point localization, mainly there were two steps. Once the key point candidate has been found after performing or after finding the scale space extrema, we have actually found the location and the scale of the interest points. Now the next step is to find the Hessian matrix, and the main aim is to reduce or to eliminate the edge responses which are there in the images. So moving on from here,